How does an entire volcanic arc seem to exhale at once? What hidden choreography in the deep earth could coordinate 6 separate magma systems so closely that, within the span of a single week, in the first week of December 2025, Fuego, Arenal, Poás, El Chichón, Yojoa, and Masaya all moved from simmer to eruption? Is this the tremor of a single giant source, or the whisper of many small ones finally reaching a common breaking point? Those questions go to the heart of how magma is born, stored and freed, and the answers lie in a cascade of geologic processes that operate from the subducting slab to the final burst at the vent. Beneath all 6 volcanoes lies the same fundamental engine, subduction-driven melting. Along the Central American margin, an oceanic plate dives under the continental plate, carrying with it hydrated minerals and sediments. As the slab descends and heats, those water-rich minerals undergo metamorphic reactions and expel volatiles. The released fluids lower the melting temperature of the overlying mantle wedge, producing partial melts that are the raw material of arc magmatism. Those melts are often basaltic when they first form, relatively low in silica and mobile, but as they ascend through the crust they can evolve into more silica-rich compositions through crystal fractionation, assimilation of crustal rocks, and magma mixing. That petrologic evolution is central to the differing behaviours exhibited by the 6 volcanoes that acted in concert in December 2025. Magma composition governs viscosity and gas behaviour, and those 2 parameters largely dictate whether an eruption will be effusive, explosive, or somewhere between. Low silica basaltic melts are runnier. Gas bubbles nucleate and escape relatively easily, producing persistent lava lakes, fountains, or strombolian bursts. Higher silica andesitic melts are stickier, they trap volatiles, permit greater overpressure to develop, and fragment violently when the gas supersaturation threshold is surpassed. In our synchronized episode, that means Masaya and Yojoa, with their more basaltic character and open conduits, tended toward fountaining and strombolian activity, while Arenal and El Chichón, with their more viscous andesites and episodic dome-forming histories, produced more explosive ash-rich behaviour. Fuego, although basaltic to andesitic depending on the pulse, favoured dense pyroclastic currents when fragmentation was intense. Poás showed a third archetype entirely, the hydrothermal, phreatic or phreatomagmatic explosion, where the presence of a crater lake turns thermal energy into steam-driven blast. But composition alone does not explain synchronous timing. Magma must be stored, pressurized, and poised to erupt. Whether it does depends on the architecture of the plumbing system and the instantaneous stress state acting on that architecture. In many volcanic systems, magma resides in a distributed set of reservoirs and sills at a range of depths, from deep crustal mush zones where crystals and melt coexist, to mid-crustal chambers that act as staging areas, to shallow lenses just a few hundred meters beneath the edifice that pressurize and feed the conduit. These reservoirs are dynamic. They accrete new melt by recharge, evolve by crystal settling and chemical differentiation, and modulate pressure through degassing and crystallization. A recharge event, the injection of hotter, more mafic melt into a crystal-rich reservoir, can dramatically change its physical state. The hotter recharge melts can remobilize crystals, reduce viscosity, and drive volatile exsolution as the mixed magma becomes less capable of dissolving water and carbon dioxide. Those exsolved volatiles form bubbles. If bubble nucleation accelerates and bubbles coalesce into a connected gas phase, The magma's compressibility increases and pressure can be transferred much more efficiently toward the conduit. A rapid change like that can push an otherwise stable system past its fragmentation threshold. The fragmentation threshold itself is a mechanical limit. Magma will fragment into ash and gas when the stresses from bubble growth and overpressure exceed the tensile strength of the surrounding magma and rock. That threshold depends on the magma's viscosity, crystal content, gas fraction and conduit geometry. A narrow conduit restricts flow and fosters pressure build-up. A wide open throat allows gas escape and tends toward effusion. In a region of closely spaced volcanic centers, local differences in these properties can mean the difference between a fire fountain and an ash column. Therefore, if several volcanoes are simultaneously being recharged or are in late-stage pressurization, a regional perturbation that slightly alters the stress field can act as the final straw. What kinds of regional perturbations can do that? Large tectonic earthquakes are a common candidate. Seismic waves passing through magma reservoirs impose dynamic stresses that oscillate at a range of frequencies. Those transient stresses can encourage bubble nucleation in supersaturated melts, destabilize fragile dome plugs, or open pathways in caprocks through remote fracturing. The effect is not universal. Only volcanoes already near critical conditions will respond. A broad analogy is a pile of kindling, where a gust of wind may kindle only the most arid twigs. In the synchronized December sequence, the most plausible picture is that each volcano had been quietly charging, years to decades of magma influx, degassing episodes and hydrothermal pressurization, and some regional stress pulse, whether seismic or tectonic, nudged all of them across their respective thresholds within a short time window. The mechanics of how seismic waves interact with magma are subtle but instructive. Dynamic stresses from passing waves generate pressure fluctuations in the surrounding rock. Those fluctuations can alter the solubility of volatiles in melt. Pressure drops reduce solubility, prompting rapid exsolution and bubble growth. In a supersaturated melt, new bubble nucleation often requires an energetic perturbation to overcome surface tension. Seismic shaking supplies that energy. At the same time, repeated cyclical loading can fatigue caprocks and seals, producing new fractures or opening pre-existing ones. A freshly opened fracture can act as a pathway for pressurized magma and gas to ascend, reducing the confinement and allowing magma ascent rates to accelerate. Rapid ascent further decreases pressure, driving still more exsolution and leading to runaway fragmentation. This coupling of mechanical stress, volatile physics and ascent kinetics is how shaking at distance can produce eruptions at discrete sites. Another potent trigger is magma mixing itself. When a deep, hotter basaltic pulse intrudes into a more evolved, volatile, saturated andesitic chamber, chemical and thermal contrasts create disequilibrium. The injected basalt may be undersaturated with respect to volatiles at depth, but will exsolve gases as pressure changes occur during mingling. Moreover, thermal shock can cause crystals to disaggregate, changing the effective viscosity and permitting faster ascent. In such cases, the arrival time of the recharge pulse determines the timing of eruption. If a regional tectonic event simultaneously opens conduits or reduces regional stresses, the combination of recharge and mechanical relief can synchronize multiple nearby systems that are all experiencing similar recharge patterns because they share input from the same subduction-fed mantle source. At the conduit scale, ascent dynamics determine whether eruptions will fragment explosively or flow. As magma rises, pressure decreases and volatiles exsolve. Bubbles nucleate on crystal surfaces and grow by diffusion of dissolved gases. If the ascent is slow, bubbles can escape via permeable pathways or form a foam at the top of the reservoir that degasses quietly. If ascent is fast, bubbles grow rapidly and coalesce into a continuous gas phase that accelerates flow. The transition from bubbly flow to gas piston, or violent fragmentation, is governed by Reynolds-like and capillary-like dimensionless numbers that account for viscosity, gas fraction, and conduit size. While the math is complex, the concept is intuitive. Sticky magma with trapped gas will build pressure until it ruptures. Mobile magma will let gas out and produce fountains or lava flows. Each volcano in the December episode exhibits a variant of these processes. Fuego, with its relatively mafic compositions and established shallow conduit system, tends to respond quickly to changes in pressure. When fresh gas-rich magma ascends beneath Fuego, it commonly produces Vulcanian to Strombolian pulses that can escalate into sustained pyroclastic currents if fragmentation is extreme. The dense, hot avalanches are the product of column collapse or dome collapse. When fragmented magma and gas cannot maintain buoyant columns, they collapse under gravity into fast-moving density currents that scour the flanks. From a mechanics perspective, pyroclastic flows are gravity-driven granular fluid mixtures whose mobility is controlled by mixture density, basal entrainment, and rheology. A sudden increase in erupted mass flux, driven by rapid degassing and fragmentation, makes column collapse more likely. Arenal and El Chichón typify the andesitic, dome-prone end of the arc. Viscous magmas at these volcanoes can form dome complexes that grow slowly and then fail catastrophically. Dome growth constricts vent geometries and traps gas. The oversteepening or internal pressurization of a dome can lead to collapse and lateral blasts. Internally, the magma may undergo crystallization driven overpressurization. As crystals grow, the melt volume changes and volatiles are squeezed out into bubbles that increase pressure. If a recharge event injects hotter magma beneath a viscous dome, the thermal contrast liquefies the plug and promotes rapid ascent. The mechanical failure of a dome is therefore a complex interplay between creep, tensile failure of the dome carapace, and rapid degassing in the conduit. The result is often ash-rich Plinian or subplinian columns and wide-ranging pyroclastic density currents. Poás demonstrates the power of hydrothermal mediation. When a crater hosts a shallow acidic lake, magma does not have to reach the surface to produce a violent blast. Instead, the transfer of heat and gas from a shallow intruding body or from a conduit that channels hot rock fluids into the lake induces flash boiling. The sudden phase change of water to steam generates enormous pressures because steam occupies a vastly greater volume than liquid water at the same mass. Those pressures can rupture overlying rocks and eject a mixture of water, rock, and altered hydrothermal materials in a phreatic explosion. Phreatomagmatic activity, when magma interacts directly with external water, adds fragmentation by thermal quenching and explosive interaction, producing fine-grained ash and characteristic surge deposits. The geometry and depth of the lake, the permeability of the crater fill, and the chemistry of the hydrothermal system control whether such eruptions are mere steam blasts or escalate into magma-water-driven explosions with significant ash production. Yojoa, long quiescent in the Holocene, reminds us that volcanic fields with basaltic scoria cones can awaken with minimal premonition. Basaltic fields are often fed by small shallow dikes that cut through the crust and erupt at multiple vents. Because basaltic magma is often volatile-rich and less viscous, even modest pressurization can produce strombolian bursts and short lava flows. The formation of a new scoria cone through successive strombolian explosions is a relatively low-volume but high-frequency process. Each burst ejects incandescent clots that build a cone. The shallow nature of these systems also means they can respond rapidly to stress changes. An opening in a crustal fracture system can allow a new dike to propagate and erupt with little warning. Masaya occupies a middle ground as a basaltic caldera complex with persistent degassing. Its broad caldera houses multiple vents and sometimes a lava lake that continually expresses gas. A persistent degassing state implies an open system that can relieve pressure, but it also hosts transient, explosive behavior when conditions change. For example, a temporary sealing of degassing pathways by spatter-built crusts, or the accumulation of a more viscous slag layer, can trap gas until a critical point is reached. When that seal breaks, the release can be strombolian to Hawaiian in style, with fountains and spatter. Additionally, if deeper recharge occurs with volatile-rich mafic magma, the interplay between the open, shallow degassing system and the new pulse can produce energetic bursts that project spatter and ash. Across the arc, the role of sulfur and other volatiles is more than a chemical curiosity. It is a key to magma behavior. Sulfur dioxide and hydrogen sulfide exsolve at different pressures and temperatures, and their release plays an outsized role in dictating magma redox state and the stability of sulfide phases. The liberation of volatiles changes magma density and viscosity and can produce corrosive acidic gases that alter crater lakes and hydrothermal systems, sometimes catalyzing further instability. In the December sequence, spikes of gas emission would be expected as fresh magma breached shallow systems or as lakes boiled, each spike signalling volatile release at depth. Another critical mechanism that could help synchronize eruptions is stress transfer through crustal deformation. The crust beneath the volcanic arc is not a static block. Dike intrusions, slow slip events, and aseismic creep can redistribute stress over tens to hundreds of kilometers. A dike propagating beneath one volcano produces a strain field that loads neighboring fault and magma systems. If multiple reservoirs are already close to failure, that elastic strain can reduce the effective normal stress on seals and faults, promoting fracturing elsewhere. In a broad sense, the arc behaves as an elastic plate in which local events can have regionally felt consequences. The December episode likely involved such stress transfers superimposed on each system's internal evolution. Finally, the ultimate manifestation of these processes, the form of the eruption at the surface, is a matter of conduit geometry, ascent rate, and volatile content. Fast ascent with high gas fraction results in high columns and fine ash that can be widely dispersed. Slower ascent or efficient degassing produces lava flows and coarse scoria. When magma fragments into particles fine enough to be fluidized by gas, density currents form and travel downslope at high velocities. These pyroclastic currents are among the most destructive products of explosive volcanism and are controlled by the interplay of gravity, fluid dynamics, and sediment transport. The deposits they leave reveal telltale signs of eruption dynamics. Welding indicates high temperatures and deposition rates, while well-sorted pumice-rich layers indicate sustained Plinian columns and long-distance transport. Putting all of this together, The synchronous eruptions of Fuego, Arenal, Poás, El Chichón, Yojoa and Masaya in the first week of December 2025 can be interpreted as the outcome of a common tectonic and magmatic context that primed multiple systems and a regional perturbation that tripped them nearly simultaneously. Beneath the arc, the subducting slab provided a steady supply of melt. Within the crust, reservoirs evolved, recharged, and degassed on their own tempos. And across the crust, stress redistributions and seismic perturbations provided the final impetus. Each volcano then expressed the built-up energy according to its magma chemistry, storage geometry, and surface conditions. Basaltic fountains and scoria cones at Yojoa and Masaya, explosive dome-related or Plinian pulses at Arenal and El Chichón, dense pyroclastic currents at Fuego, and hydrothermal steam blast behaviour at Poás. In the months and years that follow such a clustered episode, geologic records will be passed to extract the relative timing of intrusions, the chemistry of erupted products, and the deformation history recorded by ground and satellite sensors. Petrologic analysis of ash and pumice will reveal whether deep recharge mixed with evolved magmas. Seismic catalogues will be searched for a triggering earthquake or a sequence of tremor that preceded the blasts. And models of bubble nucleation and conduit flow will be used to reconstruct ascent rates that produced the observed deposits. That forensic synthesis will elucidate which triggers were local and which were regional, and it will refine our understanding of how volcanic arcs can sometimes behave like ensembles rather than isolated actors. For now, the geological narrative is clear in its broad strokes. Arc magmatism, born of subduction, supplied volatile rich melts. Reservoirs across the arc stored and evolved those melts until they were metastable. And a regional perturbation, mechanical, thermal or hydrological, altered the delicate balance, provoking multiple eruptions within days of one another. The precise choreography of recharge pulses, stress transfers and conduit failures will remain the subject of detailed study, but the underlying mechanics, fluid generation in the mantle wedge, volatile exsolution, overpressure and failure of confining rock provide a robust framework. The Earth's deep plumbing is interconnected in ways that only reveal themselves during extraordinary episodes. The 6 eruptions of early December 2025 are another vivid lesson in how networks of molten rock, gas and brittle crust can conspire to produce synchronous geological spectacle. If you found this breakdown valuable, don't forget to hit like, share this video with someone who needs to see it, and subscribe for more deep dive reports. And make sure you tap that hype icon so this video can reach an even wider audience. Your support helps keep these investigations going.